This video is about negative feedback amplifiers. It corresponds to section 19.2 of Applied Analog Electronics. Well, technically, just to the first part of section 19.2. Negative feedback amplifiers are one of the three main concepts in this class, after voltage dividers and complex impedance. And in fact, the way we usually use them, we will see both voltage dividers and complex impedance involved in doing negative feedback amplifiers. So in a sense, it contains everything we do in this class, which is part of the reason why this backdrop we've been using for all the videos is a negative feedback amplifier. Let's redraw that amplifier and analyze it. Okay, we have got an op-amp. Now, one can analyze the notion of negative feedback amplifiers without having something as nice as an op-amp as our building block, but because we do have op-amps as our building block, that's the one we're going to look at. We'll have a positive and a negative input, plus and minus, and we will have an output. The output will be the output from our entire system. The positive input will also be an input for our entire system. We'll call that one VP for the plus one. The negative one, however, does not go directly to an input. This is where the negative feedback comes in. We're going to have feedback to that point. So what I'm going to do is introduce two impedances here. One between this node and the other input. Let's call this node that's at the amplifier here VMA. That's for the minus input to the amplifier. And then we're going to have another feedback, another impedance here for feedback. And let's give this a name. We'll call this one ZF, and we'll call this one up to the input ZI. So F for feedback, I for input. These impedances can be arbitrary complex impedances. We can build them out of inductors and capacitors and all sorts of other components. Or they can be simple resistors, which is usually what people do first when they're analyzing these. But the math is the same whether they're complex impedances or real resistances. So we might as well just keep them as complex numbers for now. They're just going to be letters. Okay, how do we analyze this whole system? Well, we need to know what the different parts of it are doing. We'll need to have a formula for what the op-amp does. And we'll also have to have some formula for what's this intermediate node here, VMA. What's it doing? And one of the nice things about using op-amps as our building block here is that the op-amp has some really nice characteristics, like the inputs to the op-amp don't require any current. They don't take current, or negligible amounts. And so this pair of impedances here, there's no current coming from the point in the middle between them. So it's a voltage divider. We can use our voltage divider equation. In fact, we can use the symmetric version of the voltage divider equation. That's probably the easiest way to write that one. And say that VMA is equal to ZI times Vout plus ZF times VM divided by ZI plus ZF. And the formula we have for the op-amp, we did that in a previous video. We have Vout minus Vmid is equal to A, the open loop gain under the amplifier, times the plus input, Vp, minus the negative input, VMA, and then there's this offset voltage, which we wish was zero, but often isn't. Okay, and VMA, we've got a formula for here. I could plug it in here, but that formula looks kind of messy. And so what I'd like to do is to simplify that formula just a little bit, just to make the algebra easier to do and less likely to make a mistake. And that is to use the voltage divider formula that we had before, Zi over Zi plus Zf. It's the gain of a voltage divider. And let's just call that B. We can now simplify this formula for VMA because notice I've got Zi over Zi plus Zf times V out. So that's B times V out plus, and then over here, well, Zf over Zi plus Zf is just 1 minus B, and that's times Vm. And now I can write this whole thing out as V out minus V mid is equal to A times Vp minus B times V out minus 1 minus B times Vm minus V offset. That looks pretty nice, but we got V out on both sides. That's not so nice. So let's move the V out over to the left-hand side, and let's move the V mid over to the right-hand side, and get this thing as V out, and then we're going to have the 1 here, and we're going to be adding another AB to that, so 1 plus AB, times, okay, that's going to be equal to A times Vp minus 1 minus B Vm minus V offset plus V mid. Looking a little better. We can take the 1 plus AB over to the other side and just get V out equals A over 1 plus AB times Vp minus 1 minus B Vm minus V offset plus V mid over 1 plus AB. And that is our general formula for what a negative feedback amplifier does. And it looks kind of messy. It is kind of messy. Luckily, there's things we can do to simplify it. One is that op-amps are usually used with an open loop gain that is huge. Now, we don't always get that, which is why we sometimes need this general formula that includes the open loop gain. But it's interesting to see what happens as A goes to infinity. How does this formula simplify? Well, as A goes to infinity, AB goes to infinity, and 1 plus AB is basically just AB. So this A over 1 plus AB will go to just 1 over B. And this 1 over, or V mid over 1 plus AB, is basically going to go to 0. So we'll get, if we take the limit as A goes to infinity, we're going to have V out is, well, this is going to be 1 over B, and that's going to disappear, so we'll just have Vp minus 1 minus B Vm minus V offset over B. And that now is starting to look more like the sort of thing we would want to see. For example, we could take the Vm times B over B here and move it outside here to say that this is equal to Vm plus Vp minus Vm minus V offset over B. Now that's a very simple thing because the Vp minus Vm is the thing we want to amplify, and the offset is basically just a small adjustment to Vp. And so we have Vm, so there's a constant out here. What if we want to, say, take Vp out instead of Vm? Could we do that? Well, if we do that, we get V out equals Vp. And what are we going to have here? Well, if we take a Vp out, that's going to be putting a minus B in there. So we're going to get this is VP plus, and then we're going to have VP times, well, we've got the 1 there, but we just subtracted, we've got to subtract the B times VP off, minus VM times 1 minus B, minus V offset, over B. So that's VP plus VP minus VM times 1 minus B over B minus V offset over B. Okay, so and if you wanted to get this thing in terms of 1 minus B over B, we could go just a little bit further here and say this is equal to VP minus V offset plus VP minus VM minus V offset times 1 minus B over B. So in both cases we've got a gain here. Here we have a gain of 1 over B, and here we have a gain of 1 minus B over B, times the thing we're trying to amplify, VP minus VM, with that annoying little offset in there, and it's referenced either to VM or VP minus V offset. And so those are the formulas we most often use with negative feedback amplifiers. Quite often when people are doing this, they will rewrite the B back in terms of ZF and ZI. And we'll look at that in a little more detail in a subsequent video. This is a good place to take a break after all that algebra.